colleagues. I'm very glad to make this presentation because I'm working all my life in induction heating, beginning from 1958 when I was still a student. And now I'm talking about heat treatment of automotive parts. It's a special area of heat treating, induction heat treating technology. And the main topics I would like to talk to you about, it's induction heat treating of automotive parts, basics of induction heating and heat treating, magnetic flux control in induction coils, computer simulation and optimization, advanced design of coils and processes, induction coil manufacturing, and give you a couple examples of induction heat treating. First, it's a crankshaft hardening, and then axle shaft heat treating. This stresses and distortions issue, and finally conclusions. The benefits of induction heating are well known, but what are the special benefits related to heat treating of automotive parts? First of all, it's the process very favorable for production environment. It's easy to have inline heating. There's no pollution. There's push-button performance with immediate startup of equipment. Very good controllability and repeatability of the process. Better metallurgical results due to fast and clear heating. Predictable and well-controlled residual stresses. This is a very important point. Less and better predictable distortion as a result of the previous. Short heating cycles and high production rates. Energy saving due to selective and efficient heating. Minimum surface oxidation, almost no oxidation, and decarburization. Small equipment footprints. I want to say that in some cases we can achieve desired results only by using induction methods. Talking about the passenger car, I was preparing this presentation and I was myself amazed how many mechanical parts are subject to induction heating. It's more than 50% of all mechanical parts. And they include the parts from engine, steering, suspension and brake, transmission interior, and body and exhaust. The main parts, the classical parts for automotive heat treating, it's a crankshaft, camshaft, it's steering components, and axles and gear. What are the challenges of induction heat treating for automotive parts? First of all, it's very high liability and therefore in need of strong quality control. Second is a strong global competition. As a result of that is a permanent demand for improvements and saving. Very high production rate. In 2015, worldwide, 68 million passenger cars have been produced, with 21 million only in China. High demand for the coil lifespan, 100,000 cycles. When the customer has, for example, 50,000, they, in many cases, ask for more. Give us 300,000. And finally, very important point is that now we have evolution in car design and in industry in general. For example, due to introduction of electric cars, where the parts are different, and we need to reconsider, develop new induction heating processes. How can induction technology meet all these challenges? I want to pay your attention to the ideology formulated here in Detroit maybe 15, 20 years ago. It's designed for induction heating. It means that the designer, when makes specifications for the part, the heating, and designing the parts itself, need to keep in mind and take into account specifics of induction heating. It's related to selection of steel types. You know that there are steel types that are very favorable for induction heating. It's a carbon or low carbon steels. Then it's steel quality, grain size are one of the points. Again, you know that for fast induction heating, the grain size must be very small in order to have fast transformations during the heating. The part shape and geometry. When designing the part, we need to keep in mind how easy or difficult it will be the heating of this area. Hardness specifications. Again, it's well known that using induction heating, we can obtain higher hardness than using the furnace heating. Couple, 2-3 units of the HRC. Sequence of operations. And finally, but very, very important, it's account for treatment stresses. I need to talk about induction heating phenomenon. There is a special theory of induction heating, but of course I have no time to, and it's not necessary to talk about that to you now. I want to pay your attention to several key points. Induction heating is a contactless method based on energy absorption from the alternating magnetic field generated by induction coil. Induction heating is based on two tightly coupled phenomena, electromagnetism and heat transfer, with their well-developed theories and fundamental equations of Maxwell and Fourier. There are other multiple related phenomena such as structural transformation and so on, and multi-physics program of different level can treat these tasks of induction heating. Anyway, to use any program, the user must understand well the physics of induction heating. I want to give you some rules that all induction people of all levels must know. First, all currents flow in closed loop. It's a law of physics. We need to provide path for the current of coil and imagine closed loops in the parts for induced eddy currents to flow. The second point, inductors ampere turns are the source of magnetic field. Lines of magnetic field go around the conductors and that carry current, and they are always closed. It means that we have external magnetic field which could affect negatively on the surrounding components. At the same time, there is an area of this return path, as we call it, where we can control the heating, changing intensity of heating and distribution of field. We call it magnetic flux control. Part of generated magnetic field in the work area penetrates into the part. Variation of this field in time generates electric field or voltage in the part according to a law of induction of Michael Faraday. That's why the method is called induction heating. And the induced voltage equal to 2 pi f phi, where f is frequency and phi is magnetic flux value. Generated voltage causes eddy current flow in the part that hits it due to resistance of the material. We can control heating by the coil design, frequency, and power via the coil current. It looks like very simple, but maybe not very simple, because the materials that we heat, they may be magnetic. In automotive parts, they are almost all magnetic, and the phenomena in penetration of electromagnetic field in magnetic materials are rather complicated. In general, magnetic field penetrates into the part and attenuates, there is certain legend and myth that the current inside of the part changes from the surface according to exponential law. This could be true in some cases, but not always. And I'll show you later what happens really when heat treating automotive parts, surface hardening. Measure of attenuation called the reference penetration or skin depth delta. Delta depends upon field frequency, material resistivity, and magnetic permeability. And for hot steel, for non-magnetic states, which is the final stage of heating for heat treating, for austenitization, the formula is delta equal 500 divided the root square of frequency. And for frequencies widely used for automotive industry, it's a range from several kilohertz up to 100 kilohertz. This reference depth is from 10 millimeters up to 1.6 millimeters. And it's very essential to make proper selection of frequency for heat treating in general, and specifically and especially for surface hardening of complex geometry in order to have the contour hardening of gear as we see here on this wonderful picture. In general, for good initial approach for fast and efficient heating, we can assume that we can select that the reference depth must be 1.5 to 2 times larger than required hardness depth. For example, if we need to have hardness depth 4 millimeters, it means that the reference depth should be 8 millimeters, something 6-8 millimeters, which corresponds to frequency about 3.5 kilohertz. This is the optimal, the values of frequency. Now, let's look a little bit on power density and temperature distribution during the part of simple geometry, for example, rod heating. Here we have the curves of the power distribution, watts per cubic centimeter, for different stage of heating. Here's the radius, and this curve corresponds to the beginning of the process when the part is completely magnetic, and you see that it drops very quickly. It's not exponential, but it's some kind of parabolic or even linear. When the temperature of the part grows up, so we'll have this green line due to change in resistivity and permeability, but the part is still magnetic. Here we have at this curve, at this point, we have non-magnetic transformation, non-magnetic layer of material on the surface, and the curve of power distributions change dramatically. From here then to here, when the non-magnetic layer with temperature above the Curie point gets thicker. And the final ideal distribution for surface hardening is this red. Here there is a desired hardness depth, and approximately here we have a point where Curie point is achieved in material, and here inside magnetic material, and outside here non-magnetic austenitized material. Here there is a corresponding the temperature curves, and the final curve shows us that we have at the depth, hardness depth, we have above, slightly above 800, when in the surface we have approximately 930 centigrade. That's very important that the current temperature distribution in the area of hardening is almost rectangular, and there is no overheating of the surface as it happens in the case of flame heating, for example. Now, I mentioned about necessity of strong control of induction hardening. In addition to traditional control such as the reading of a pyrometer, we can use the unique feature of induction heating, which is the dependence of coil parameters on the load, the part conditions, on dimensions, cracks, off-center, temperature, etc. For example, if you place here a wrong part with a wrong size, you can feel immediately the change in parameters, and the control system can say, oh, that's the wrong part. The same can happen if in the process of heating or initially there will be crack. With a proper control system and sensors, you can identify these conditions and reject these parts. Corresponding frequency, current, and voltage sensors are widely used for process monitoring and control. Modern power supplies may be set for operation at constant or programmed variation of voltage, current, and generator power, which allows us to control or optimize the process. I want to mention a little bit, talk a little bit about magnetic flux control. I said that the magnetic flux passing through the working area must return back outside. If we place here some magnetic material, which we call magnetic, controller or concentrator, we can significantly change the amount of flux flowing here for the same current, and we can change the distribution of temperature here. These two pictures show you the magnetic field lines and the color map of temperature for the same coil current. You can see that with the concentrator we have better shaped the heating zone and much higher temperature than without. Especially this phenomenon is important for internal the induction coils, because in this case magnetic flux must return back inside of the coil with limited cross-section, and the presence of magnetic controllers can significantly influence and improve the heating. Here there is an interesting example of effect of magnetic concentrator. The special installation was made for demonstration of effect of concentrator. We have here the hairpin coil with the two portions. One is without concentrator, another with the E-shaped concentrator. Of course, the current here and here is the same, but we can see that in this area temperature is very good, and here there is almost nothing. And computer simulation confirms that. Actually, it was the whole demonstration, the case was designed using this computer simulation. Now, what materials could be used for magnetic flux control? There are three traditional materials. It's laminations, sheets of electrical steel, ferrites, and newer materials, soft magnetic composite. I want to say that ferrites are almost not used in induction heating automotive parts due to several drawbacks. Traditional material is lamination. The material stamped or machined pieces of laminations are installed between the copper keepers and work provide proper effect. Newer materials, soft magnetic composites, have excellent machinability, good saturation, and ability to work well in 3D magnetic fields in any frequency used in induction heating. Now, about the installations. The installations may be of three types: distributed, mounted in a single platform, and built in line. But in any case, the whole installation has these following components, which is machine, the hardening portion with the induction coil, quench system, then machine control, heat station, power supply, and water cooling system. In the case of distributed the system, you can use separately existing machines or different non-special machines and incorporate inside or keep separate power supply from the high-frequency generators. Here's only examples of power supplies from company AFD Induction. This one is with two outputs independently controlled, each 40 kilowatts. In this case, we have a long-standing power supplies with a much higher power. The machines themselves. Here we have a machine typical for automotive parts. Due to the high production rate, the OEMs, they try to make special machines which incorporate the handling of the parts, and the high-frequency components are incorporated inside of this line in this machine. This is a machine for Tulip and CV joint hardening. A similar machine is for hub unit hardening. Now, computer simulation. Computer simulation plays the high role in design of induction heating, in troubleshooting, and so on. I mentioned that induction heating, induction hardening is based on main two processes, electromagnetic and thermal. But in reality, we have much more processes. First of all, in modeling, we need, in many cases, keep in mind the process control, power supply circuits, machine operating mode, for example, variable frequency of scanning, and so on. Then we can simulate structural transformation that happens in the process of quenching and heating and quenching. And then stresses caused by electromagnetic process, by thermal expansion, by quenching structural transformations. All these factors, they create stresses varying in time. And we have, at the end of hardening, we have residual stresses in the part and some distortions. These distortions and stresses, they influence on the final quality of the part, and we can, in many cases, simulate also how they influence on the service of the part. So we can simulate the loading. The theory of computer simulation is rather complicated. There are many sources for that. You can look inside. I want to only to mention quickly the 3D simulation, 2D, and 1D simulation. Actually, each induction coil, induction system is 3D, but in many cases we can simulate them in a more simple way as a 2D on 1D. Here we have the example of the heating of gear, one part of the tooth, in the circular induction. You can see that the power density is distributed non-uniformly, not only in circumference but also in the length of the tooth. That's the effect of three-dimensional field. 2D simulation for axle shaft hardening. We made a big study of this technology of heat treating of axle shafts, starting from the reproduction of traditional heat treating processes using two-turn coil with a smashed copper tubing. It's very simple. It's a cheap coil. It's widely used. But there are two big drawbacks here. One is it's difficult to have proper heating of the flange, fillet area. If you want to have proper heating here in this area, you'll overheat this portion of the stem with the proper defect in the part. We designed a new coil, two-turn also, but with different configuration of copper and the presence of magnetic controller that can focus heating more on the flange without overheating of this area. It's example of 2D simulation. Now, in order to, in simple cases, or as a preliminary stage for simulation, we can use even more simple 1D approach. Example is heat treating of the shaft end with diameter 40 millimeters and hardness depth 4 millimeters. That's how it could be heated, and that's what we desire to. We need to harden that and then temper that and finally cool. We, by simulation using 1D program ELTA, we found that the minimum time for austenitizing is 4 seconds at optimal frequency of 3 kilohertz. This time was selected as a base for other stages. For austenitization 4 seconds, 8 seconds, 2 stations for quenching, 2 stations for tempering, and then two stations for, or more stations for final cooling. The installation could be made as a linear or rotary table type. Here we have the results very well the presented distribution of temperature in the radius of the part during all the stages of processing. Here we have the heating, then we have 1 second transportation to quenching, the first stage of quenching, the transportation, the second, and so on. Pay attention that tempering time is very short, only 8 seconds, the same as we have for quenching time. And at the same time, we provide here very uniform temperature distribution in the part. And that's partially due to the fact that we don't cool the part during quenching completely. Some residual temperature, about 200 C, remains here in the center and support heating in the tempering stage. Here we have distribution of the power of the temperature on the surface in the center and at the depth of desired hardness. We can see here that the temperature of the center is more than 200 here when the part is moved to the tempering stage. Now, induction coils. How to make good coils. When I started my career, my work with induction, it was many times ago in 1958, one old coil master said, "Valentin, keep in mind that it's difficult to make a coil that doesn't heat at all." And it's true. If you have some loop of copper and that carry current, you can have some heating. But In order to have the good coil, you must meet specification to temperature distribution, have a satisfactory lifetime, provide desired production rate, have good electrical efficiency, have favorable parameters for power supply in order to match that to the power supply, meet special requirements such as quenching supply, atmosphere, material handling, incorporation into the machine, etc., and have a reasonable cost. I intentionally place that to the last the point of the list, because usually any improvements, real improvements in the coil at additional cost will pay back very quickly. In many cases, induction magnetic flux controllers are required to achieve these goals. This is a very simple example. This was the initial really the coil used for low temperature heating of the end of the shaft. There was bad performance. It was the heating of the part, the turns and damaged that. So we designed this coil. Of course, it's much more expensive, but it worked excellent. Now, coil manufacturing. After we made the initial design based on the previous experience on computer simulation, we need to manufacture the coil. The traditional manufacturing is in bending. Here it's very simple bending the coil. And for more complex inductors, we braze machined and bent parts and then apply concentrator. Here you can see the bent the portions here, and they are connected in one assembly with multiple brazing the seams. An example of such a coil, the assembly for heating multiple cams of the camshaft. Magnetic shields here prevent mutual influence of individual position and improve heat pattern. One more example of different technology. It's a coil with completely machined copper body. There are no the welded or brazed seams. And machined body provides high accuracy, high mechanical strength, and reliable performance. You can see here also the side shields that play three roles. Crankshaft web shielding, heat pattern control, and coil efficiency improvement. Finally, the newest technology, which are at the emerging now, and it's proposed now by GH Induction. It's additive manufacturing and microfusion. You heard at least about the advantage of additive manufacturing, and these technologies could be applied to manufacturing of the coil of very complex geometry using 3D printing machines and the electron beam the melting. Here there is an example of several coils sitting on the working plate of the machine. The other technology is microfusion. In this case, wax model is made by 3D printing, and then microfusion happens using silver or silver alloy materials. Advantages of this technology is repeatability due to improved accuracy, increased lifetime due to optimal cooling and absence of brazed seams and related flaws, consistent quality. I don't know exactly about the price. Probably this is the point of compromise. In some cases it will be more effective in sense of price, maybe in some cases not. But of course we can use also combination of traditional the manufacturing methods and the newest. Here we have an induction coil for single shot hardening of the shaft. The central zone of this coil is made by traditional methods, and the end zones have the microfused, the complex geometry portions which are braced to the central one. Here's the picture of the coil in performance. During manufacturing, in any methods, in traditional, for example, we need to follow several rules. First of all, in order to have good lifetime in performance, we need to have good coil design. It's the imperative. The second, we need to use high quality materials. Copper, it's pure oxygen-free or silver-bearing copper. Concentrator material of good quality if required. Insulation and coatings also when required. We need to use best manufacturing technique. For example, tube bending could result in some the change of profile and not good cooling and so on. Brazing is a very, very important point. This is a source of many failures of the coils. Never use soldering except of not water-cooled, some low-power coils. Machining quality and some special such as considered before. We need to pay attention to installation of the coil in order to provide mechanical protection and avoid any impact of the part or some mechanical impact on the coil. Maintenance. Maintenance is actually, it's relatively simple. First of all, we need to watch water cooling. We need to control pressure, temperature of water, quality of water, of cooling agent, flow rate, and build-up control. I know, for example, practice in some companies, they weigh the inductor before installation when it's manufactured, and this is a certain weight of that. After a certain time, they remove that from the machine and they weigh again. And they can see, for example, that weight is larger. What it happened, it means that there is some build-up maybe inside of that, or some on the top of that, and it requires the repair of a cleaning, and that works. It's preventive control. Talking about design, I want to show this one. This is a very often used geometry of profile the tubing with a nose, which is necessary for heating the angle zone of the shaft and so on. You can see that with a high loading, we can observe the copper erosion due to overheating, and computer simulation confirms that. We have here very strong concentration of power and insufficient cooling due to this pocket where there could be steam pocket and low heat transfer. How to avoid that? For example of better design for this piece is to make wider rounded pocket for better water pass, and to apply concentrator here in order to reduce the current for the same heating effect. And there are some other things that could be done in design. I want to say that the main failure of the coils is due to elevated temperature and the corresponding effects on copper and insulation and concentrators. We can predict the temperature using computer simulation. Here's an example of scanning system. We have a color map of temperature in the part and in the coil itself. So, of course, here we have different temperature scales. Now I want to show you some examples. The first part, which was used for induction heating, was a crankshaft. At the beginning of 1930s, the TOCCO company, which is the Ohio crankshaft company, they introduced this technology with very big success. The initial design was simple, very simple, and we call it the Clam-shell. Very soon, the lines for hardening have been used in different countries. For example, here there is a line in Remscheid, Germany. Pay attention to how it's different than traditional heat treating. It's very clean environment. It's absolutely different level of technology. These types of clamshell coils we continue to use, especially for the hardening small crankshaft and not high production rate. The alternative design of induction coil was proposed by company Elotherm. Here is the first test inductors of Elotherm system in 1941. It had no concentrator magnetic controller at all, but it was a very good idea. The modern inductor presented here with very well balanced heating of different portions of the surface due to copper shape and due to the concentrators installed here. With such inductors, we can provide very complicated hardness pattern as in this case. These coils could be used on the machine, multi-station, multi-position machines, such as in this picture from the website of Alfin Company. In this case, of course, the part is rotating, and the induction coils, they repeat the rotation and position of the corresponding pin. And finally, the third idea. This idea was proposed in 1960s in Russia by my teacher, Dr. Demichev. Now it's called Non-Rotational Contactless method. It was successfully used for Camshaft and then for Crankshaft. How does it work? The inductor has two halves. One is connected to the power supply and energized, and the current flows here in this coil half. The second is similar. It's a mirror reflection of the first one, but it's short-circuited. And it's supplied through the magnetic coupler, similar to local transformer, which generates in the second portion, the upper portion, the current of almost the same value, but in opposite direction. So in each position we have here the current flowing this way and current flowing that way. And in this case, we don't need to rotate the part, which is very favorable for crankshaft hardening. Recently, the company Inductor Heat made a series of inductors in special machines, the Crank Pro, for hardening and tempering crankshaft. Another example in the axle shaft hardening. I already talked about this the optimization of induction coil and process. Here I want to show you the full assembly of two-turn axle scan coil with a quench body incorporated inside of the coil. What are the results of this optimization, this improvement? In position A, it's on the stem of the shaft. We have required a case depth 10 millimeters for the same power of the coil with a scan speed 15% higher than with traditional inductor. Here it's a question not of quality, here it's of production rate. In position B and position C, we have both improvements in quality and in time. The dwelling time, the initial stationary heating of this portion, we reduce dwelling time, heating time from 10 seconds to 8 seconds. With mass production of axles, it's significant improvement. Working with this part in cooperation with the company of Dante, we simulated also the stresses and distortions created during the heat treating. And it was very interesting opportunity to simulate the whole chain of processes from hardening, tempering, and then even loading. And we call it virtual prototyping of the axle shaft heat treatment. The steps is simulation of hardening process. It's electromagnetic and thermal with Flux 2D program. And here we optimize the process in order to have faster and better quality of heating. Then with Flux 2D, we can simulate also the temperature of the coil and predict reliability of the coil. At the same time, we simulate structures, structural transformation, stress and deformation using Dante program. After that, we simulate tempering, simulation of stresses and deformation with Dante program. It could be induction tempering or the furnace tempering. And finally, torque loading test, simulation of stresses and strains using Dante program. The results are here. Here we have axle stresses after hardening. And stresses could be controlled by temperature distribution and severity of quenching. You can see from simulation that the surface area, the hardened zone, has very strong compressive forces, stresses, which is very favorable. At the same time, inside we have stronger tensile the stresses, with especially big values in this zone and this zone. And we can predict that with some, maybe in some cases we can have here internal cracks. And in order to avoid that, we can change, for example, severity of quenching and avoid the danger of cracking here. So there's a big opportunities for quality. And here we have results of simulation of loading of this shaft. Loading by applications of torque to the spline. Here, in this case, we have stresses in the axle when applied 6 kilonewton meters torque without account for residual stresses. You can see here big tensile stresses on the surface. If we make similar simulation with initially generated here residual stresses, we have absolutely different the situation. Even on the surface, we have almost neutral or slightly even the compressive stresses, which definitely can result in higher loading capacity or longer lifetime of the part. Here there is a curve, the torque, and the principal stresses without account for residual stresses RS and with account. And here the overload crack in spline zone, and we want to thank our co-author in this study, who helped us, provided us this is a result. It's from Dana Corporation, sorry. Conclusions. Induction heat treating for automotive parts is a special field of induction technology due to its specifics. Many improvements in this technology and corresponding equipment have been made during the last 15 years. Computer simulation helps to achieve optimal results much faster and more secure than trial and test methods. The most effective way of optimization is virtual prototyping based on multi-physics simulation of a chain of processes that includes induction heat treating. Advanced coil design and manufacturing is a critical point for effective use of induction heat treatment. I want to also to show you the quote to cite the opinion of a very good expert in automotive industry, Dick Collins from Borg Warner, who is now retired. But when he worked with induction technology for axle shaft hardening, he said, "I have been amazed at the testing results of the components that have broken many of the established rules of structure, carbon level, hardness, etc., of the component attributes. I completely agree that induction technology can give you quite different results than traditional heat treating." I want to thank you for your attention, and I want to thank all the people who helped me to prepare this presentation. This is the picture I like. It shows that we, with induction heating, can heat treat without special problems much larger parts, not only of passenger cars, but of big mining equipment and so on. Thank you once again.